Hello students, in this video we'll consider minimal surfaces and construct a variational problem for minimal surfaces. We say that a parameterized surface is minimal mean curvature is 0. In other words, H was 0, right? Of course, we can write H in terms of the first and second forms. Recall, of course, what H is. So H is 1/2. It's going to be L. That's this in the implemental form. And then L is hit with E, F, and then that's hit with a G. Minus 2M F plus N E, all divided by E G minus F squared, like that. That's an equation where, of course, our first fundamental form 1 is really what? Is really E du squared plus 2F du dV plus what? Plus E squared, and then 2 is going to be L du squared plus 2M du dV plus N dV, right? Our first and second fundamental forms. Great. All right, so now what I want to do is I want to show that, and this is, I want to say, give some context for when the surface is minimal in terms of the variation, right? Because minimal necessarily implies that some derivative is equal to 0. So what we're going to do is we perturb our surface. Let's let R of u v be a parameterization. Of our surface S with first and second fundamental forms. Given by that. And then what we're going to do is we're going to perturb this along the normal direction, right? So let's let H, and so both of u and v are in some parameter domain, so u can be in some parameter domain. And we'll let H at the closure of this region D and consider a new mapping, R superscript T of u and v, which is R of u and v, and then plus T H of u and v, and half of u and v. So we're perturbing in the direction of the normal vector. So this is a normal perturbation. Okay. Now I want to find the first and second fundamental forms as RT, right? So let's write E sub t. So it's E sub t. E sub t is going to be R sub u, T sub u dot R T sub u, like that. And so now let's do it, right? So it's going to be what? It's going to be an RU plus THU n hat plus THn hat u. And then plus what? And then dot, of course, the same thing. RU plus THU n hat. And then plus THNU hat, like this, right? And so we're going to get a whole bunch of terms over here. So what terms are we going to get? Well, let's do the RU first. So if I have RU dot RU, that gives me a straight old E, right? RU dot N is equal to 0. And then RU dot NU, that's going to be a TH. And then RU dot NU is negative L, right? So that's going to be a negative L, okay? N dot RU is equal to 0. N dot N is equal to 1. So it's going to be a T squared plus T squared HU squared, like that. So if I do this dot this, we're going to get a T squared HU and the N. If I do this and this, we're going to have a T squared HU, H, and then N dot NU, right? But of course, NU is going to lie where? In the tangent direction, right? So that's going to be gone. And then we're going to have a what? And then, so of course, we can just leave that if we really want. We can just leave that. Then we're going to have NU dot RU. That's going to be a negative TL, right? So it's going to be another negative TL. So plus TH plus TH, and then a negative L over there. Then we're going to have the same thing over here with the t squared. And then we'll have a t squared and then nu dot nu. So that's going to be an nu squared, right? So I'm just going to put more things that look like t squared plus order t squared terms over here, right? Other t squared terms. That's great. All right. And so now let's do what's ft. Ft, of course, is going to be ru dot rvt. And it's going to be ru plus thu n hat plus thnu hat dot what? Dot a total of rv plus thv n hat plus thnv hat. Again, what we're going to see, we're going to have a total of an f over here. So that's going to be an f plus what? Plus ru dot, this thing's going to be 0, ru dot, this thing is going to be a negative m, right? That's going to be my negative m. So I'm going to have a negative m. Th, let's see over here, with the th, then negative m. Th, negative m. Then if I do these terms over here, that's going to be 0. That's going to be a t squared hu hv. That's going to be a, over here we're going to have a t squared h squared n dot nv, which is going to be 0. Then we're going to have a, let's see, we're going to have a nu dot rv. It's going to be a negative tn, so another one of these guys, negative mth, like that. Good. And then over here, we're going to have another t squared term. And then over here, we're going to have another t squared term. Make sure I have all the terms right. That's going to be n. That's going to give me a t squared. That's going to give me a t squared. So I'm going to put plus order t squared over here. Order t squared. Good. Eventually, we're going to do a derivative of this with respect to t, and those order t squared terms are going to be gone, right? And then finally, what's gt going to be? So gt is going to be rv dot rv, similarly, right? And so what's that going to give us over here? So that's going to give us what? Just writing it out, it's going to give us a g. The same by symmetry over here, it's going to give me a g minus a 2. To what? Now I have an n over here, an n, and then a th. Th like so, plus order t squared. Okay, good. Now let's compute the first fundamental form of this perturbed surface, right? So let's do that. So what is Eg, Et, Gt minus Ft quantity squared over here? Well, if we do those things, if I multiply these things, what's going to happen over here? So we're going to have a whole bunch of terms. But what's going to happen? What's the salient feature of these terms over here? So the salient feature is that we're going to have a what? So let's think about this carefully. So all of these L terms over here, so we're going to have an Eg minus F squared when we multiply those out, right? And then what's going to happen? We're going to have some cross terms over here. So the E's are hitting the G's. So these terms over here are going to hit these terms over here, like that. And so what terms are going to survive? The T terms are going to survive. Are going to be an L times G with a negative sign, right? So it's going to be an L times G, a negative L times GT, 2 L times GT. So of course, one of these things, right? 1. And then minus 2, well, let's not pull that out actually, let's just sort of leave it for the time being, right? So that's the first thing over there, and then we're going to have all these negative terms over here. So the negative terms, and then we're going to have 2 of everyone. We're going to have an LG, we're going to have an LG, and then those are going to have a T and an H as well, right? TH as well. And then we're going to have a minus, a factor of 2 of those things, right? So it's going to be a 2, and then these FMs, FM, and then we'll have a what? And we'll have an NE, right? Plus a 2NE. All these terms are going to be hit with what? All those terms are hit with a T and an H, right? So a T and an H. Everything else has order what? Everything else has a total of order plus order T squared. In other words, when your derivative with respect to T, those terms are going to vanish if I plug in T equals 0. Okay, good. And so if I factor this in a nice way, what does it become? This becomes Eg minus F squared. Pull that out. If I pull that out of itself, it's going to be 1. Then, of course, if I put a 2 over here, if I divide by 2 and turn this into a 4, then that becomes the what? And I pull an Eg minus F squared out of that, becomes the mean curvature. So that's going to be minus 4, and then a T, and then a little h, then the mean curvature, and then plus order T squared terms over here, right? Good. And so what does that tell me? That tells me that the area of this ET thing over here, these terms over here, are going to have what form? So my area, as a function of what? As a function of T and H, right, is going to be what? Is going to be the double integral over the parameter space D of the square root of this thing, so that's going to be a constant, EG minus F squared, times the square root of this expression over here, 1 minus 4TH plus OT squared to the power what? 1/2, right? And then we're going to have a D area element. Good. And so if I do the derivative of this area with respect to T, area of T and H, and I plug in T equals 0, what's going to happen over here? Well, if we plug in T equals 0 to this thing, the derivative of this thing over here is going to be a what? It's going to be in the numerator, I'm going to have a factor of a negative 2TH, and then the 2 is going to cancel out, so we're just going to have a factor of what? It's going to be negative the double integral of this, the T terms are going to go away, right? We're just going to have a total factor of what? We're going to have a total factor of this 2H, right? And then upper constant, of course, and then the square root of EG minus F squared dA, right? So of course, this expression over here is just my area prime of 0, right? And if I want this to be a critical point of this area functional, if I'd like to find a surface which makes this this area functional have a critical point at the origin that corresponds to, of course, just this first given surface, what do we really need? Of course, this h can be any function I wish, right? So in particular, if you have a minimal surface, if h is equal to 0, then this is a critical point of the area function. So that's one thing that's obvious, right? So if you are a minimal surface, then area prime of 0 is going to be equal to 0. So you are a critical point in this area function. In other words, you're a local minimizer of the area relative to that boundary. Now, suppose that h capital was not equal to 0. Well, since I can choose this h to be what? Since h is any continuously differentiable function, I can replace h. If I choose h to be h capital, then this becomes something like a negative 2h squared times something positive, right? Something positive. Now, if I choose h to be h and h capital was not 0, so if you're not a minimal surface, then you will not have a critical point because the derivative will be strictly less than 0 at that point. So in other words, I know that you have a critical point in this area functional if and only if you have a minimal surface. In other words, if the surface area, if the surface area is minimized, if and only if the mean curvature is equal to 0 at that point. So in other words, this idea of having a 0 mean curvature is exactly equivalent to this idea of minimizing the surface area relative to a fixed boundary, right? So if in other words, these problems occur in physics all the time, and think of like the natural state of if you have like a wire and you have the film of soap on there, the soap film will naturally, under the surface tension, will basically form a minimal surface, right? So you can actually construct this experiment, take any wire you wish, right? Dip it in a soap film, lift it up, and then you're going to find that the soap adheres to a minimal surface by the laws of like tension, laws of like the surface area, the tension, surface area, and the capillarity, and these sort of ideas in physics, right? So we've just concretely addressed the issue of saying that if you want to perturb away from the normal direction, right, of all of those surfaces, the one that has the minimal surface area is the one for which the mean curvature is equal to 0. Thank you very much.